Hi, welcome to CSE351 Introduction to Data Science, and this chapter is Mathematical Preliminaries Part 2. We have done Part 1 already. Here we will start with correlation analysis. Now the question is, why is correlation analysis important in data science? So the answer to that would be that often we want to predict the value of one field or an attribute, you can say, based on another attribute. So we want to find out how much of the predictive information do we have in one variable or an attribute X for the other attribute Y. So that's what correlation analysis will give us, will help us in finding out. So let's look at this definition that says that two factors will be correlated, and let's say that one factor is X and there's another factor Y. So we will say that the two factors are correlated when the value of X has some predictive power on the value of Y. So we want to quantify how much predictive power does an attribute X has on an attribute Y. So attribute means field. Okay, so when you know the value of X, then what can you say about Y? How much of predictive power do we have in the values of X for the values of Y? So this is something we kind of measure using correlation coefficients. So let's look at the first correlation coefficient, which is very popular. It's called Pearsons correlation coefficient. But before that, let's think about the different kind of values that these coefficients can have. Now, the correlation coefficient of X and Y will measure the degree to which Y is a function of X. So we can put it that way also. So it's kind of conveying the same thing, the same information, which is about how much information can you extract about Y from X, and vice versa. So the correlation coefficient between X and Y would be same as between Y and X, and we are kind of getting the same information, which is the predictive power of X for Y and Y for X. And the values that this correlation coefficient can take varies from -1 to 1. -1 being the lowest, 1 the highest value or a correlation coefficient can get, and in between we have 0 as well. So we need to understand what these extreme values mean. When we have -1, what does that mean? When we have 1, what does that mean? And what's 0? So when you have X and Y, and assume that X is independent variable, and using that we are kind of predicting the value of Y. So now when we have the correlation coefficient value as -1 between X and Y, then we will call that as anti-correlated. X and Y are anti-correlated. Whereas if we have the maximum possible value, which is 1 for correlation coefficient between X and Y, then we will say that they are fully correlated. Okay, and in between we can have all the possible values from -1 to 1, and the value 0 has its own significance, which will say that X and Y are not related at all. So often the students have confusion regarding uncorrelated and anti-correlated. So well, let me tell you this thing right now, and then I have a picture which I'll use to show you the different scenarios of different correlation coefficients. Anti-correlated is still a good thing, right? So if you have a high anti-correlated value like -1 or -9, -0.9, or -0.8, or you have a positive value very close to 1 like 0.9, 0.7, 0.8, then these two are good. I mean, anti-correlated information is also positive, and even the fully correlated information is also positive. Positive in the sense it means that Y is a function of X. Not exactly, but we can say that X has some predictive power for Y. Whether it's positive or negative is totally different, but still there is some correlation. If it is negative high value, that means we are anti-correlated. If it is positive high value, then that means fully correlated. But if you have the correlation coefficient close to 0, then that is a bad news. Because the correlation coefficient close to 0, that means we do not have any correlation at all between x and y. So let me take you to the next figure where we have a lot of scenarios, and I'll look at few diagrams, and I will try to explain. So here, let's start with the most, the best case. Let me put the best case. So correlation coefficient right here in this figure, if you pay attention, is 0.9. And here the number of points, the samples are 100. You have two variables, variable A on the x-axis and variable B on the y-axis. So now we will call it positively correlated with the correlation coefficient as 0.9, for the reason that if you look at the trend, then as the value of variable A increases, the value of variable B also increases. So let's start with this point. Okay, so here this is the lowest point in terms of A and B, and if when you move to this point right here, then as the value of variable A has increased, the value of variable B also increased. In this case, we do not have much increase in B. It's kind of same, whereas for most of the points, if you look at, so this is a scatter diagram with a lot of samples plotted, and we have the value for variable A and the variable B, you can see the trend. So for most of the points that we have, or most of the samples that we have here, the trend is that as the value of variable A increases, so is the value of B also increasing. So that is the positive correlation. Increase variable A, you will see a corresponding increase in variable B. So that means that there is some positive correlation between the variable A and the variable B. So let's think of a scenario like where can we have it. So how about this? If you say that, on the x-axis, if we say the smoking habit, like how much a person is smoking, and on the y-axis, if you have the mortality rate, so that I believe is positively correlated. The more the habit of smoking is, higher the mortality rate we will expect. So that is an example of positive correlation. Okay, so let's look at the negative correlation now. So here you can see that in this figure, the correlation coefficient has value minus 0.8. So the value is high, but it is negative. So what does it mean? So let's try looking at the points. So right here, we have a higher value of, let's start with this point. You have a highest value of variable A, and some value of variable B, which is not the highest. But as you move towards the left, that means as you decrease the value of variable A, you see an increase in the variable B. So that's a kind of anti-correlation, which means when you keep on increasing the value of variable A, the value of variable B keeps on decreasing, right? So all these higher values of variable A corresponds to a lower value of variable B, whereas this higher value of um, uh, variable B corresponds to the lower value of variable A. Okay, so we can have a scenario where if you have x and y as two coordinates or two variables, and you're trying to see how much you can say about y on the basis of the observation of x, then we can have the anti-correlation where an increase in x may result in the decrease in y. Okay, as an example, let me take this example from our textbook. So there has been a case where we have a negative correlation. So that means your financial status, if you are wealthy, right? So on the right, on the x-axis, which is variable A, you can think of your well-being, how well you are financially. So financially well-being is on x-axis, and your chance of heart disease is on the y-axis. So it has been found using some data set that there is a negative correlation between these factors. So that can be somehow, reasoned as well, that if the person is well-being, then that means the person is taking good care of her or his health, and which is resulting in lower risk of heart disease. Okay, so even that thing is good. If you have a negative correlation, then that is good from data science point of view, because once we find that there is a negative correlation between variable A and variable B, then we can use that for our prediction process. We can use that feature for a model building. Okay, fine. So we have seen these two extreme cases, a high positive correlation and a negative correlation. So this case here where you have correlation coefficient of 0.7, this is also a positive correlation value is good. I would say bad, because 0.7 is a good number, which is kind of showing a decent correlation in the positive direction. So fine, let's move. Let's have a look at the top figure right here. So here the correlation coefficient is very small, 0.1, which is very close to 0. So here you can see that we don't have any trend at all. Okay, so more or less I will say that variable A is not correlated with variable B at all. Right? We don't see any trend. It's kind of very random, I will say. Okay, so in the first row, if you look at, then we have very small correlation coefficient, which signifies that we don't have any strong correlation between variable A and variable B. So I found this figure interesting, as we have different scenarios corresponding to correlation coefficients. Okay, now let's move on to some coefficients, correlation coefficients, which are very popular. So we will start with the Pearson's correlation coefficient. So in the Pearson correlation coefficient, we compute that using this formula, and it is denoted by the letter small r. So here, how do we compute that? So let's assume that we have observations, we have n samples, and in n samples we have the value of x as well as y. So in order to compute Pearson's correlation coefficient, the first thing that we need to do is to individually compute the mean for the x as well as the mean for y. So we have n samples, and in these n samples the values are available for x as well as y. So these are two attributes you can call, or two features you can call in machine learning of fields. The point is that we have the measurements for x and the measurements of y. So practically x could be the height of a person, or y could be the weight of the person. We want to see the correlation between height and weight. So what do we need to do first? Let's compute the mean for x, and similarly the mean for y, mean for weight and mean for height. And then what we have to do, we need to compute this expression in the numerator, which is we need to see, for each observation that we have in x, how far is that observation from the mean. Okay, so let me take let me give you some example. Okay, so let's assume that our xi is height. X means height, okay, and y means weight. So in x variable we have height, whereas in y variable we have weight. Now let's pay attention to what we are doing. For every observation we have n samples. Total we have n samples. That means we have the data for n people. N could be 100, 50, it is up to you. Alright, so how are we computing the numerator? Let's figure out the numerator first, and then we will go to the denominator. And let's assume that x bar is equal to 160. Okay, forget about what these values are and units. I just want to get some value so that our example is meaningful. And similarly, let's assume that y bar is 175. All right, so now what we have to compute for each sample is how far each xi is from the mean. Okay, and similarly, how far is yi from the corresponding weight, mean of the weight. So if we have, say, the first sample with xi as 170 and yi as 180, then the result here, which is xi minus x bar and yi minus y bar, would be positive and positive. Okay, so this term that you have is positive. Why? Because xi that you have is 180 and your x bar is 170. And similarly, this thing would be positive because your yi is 180 whereas y bar is 175. So for the first sample, if we have, then the first sample is giving the indication that your xi as well as yi, they are on the higher side of the mean, the corresponding means. Your height is higher than the mean, and similarly your weight is higher than the mean. So the impact of these two positive terms would be a positive value, right? Positive multiplied by positive, you get a positive value. So that positive value would be added to this expression that you have. Okay, that's one scenario. So this was the first sample. Let's think of the second sample. And the second sample, we have some value like 150 and 170. So if you have 150 and 170 and you know that your x bar, which is mean of x, is 160 and mean of y is 175, then in this case your xi minus x bar would be negative, and similarly your yi minus y bar would be negative, and the result would be positive. Alright, so that's again a good news for us because you know what is happening. These values, which means that the height is less than the mean, so the weight is also less than the mean, then that means that it is in correspondence with the variation. Okay, so if x is less than the mean, then y is also less than the mean. So that will add to the expression that we have in the numerator. Okay, so now let's think about the third scenario. The third scenario would be something like, let me take 165 as the value of height and the weight could be 170. Alright, that's the third sample. So here if you do xi minus x bar, that's 165 minus 160, then this guy is positive. Okay, that means the height of the person is more than the mean. Good. And how about the weight? The weight, which is 170 minus 175, is negative. Alright, so when you do positive multiplied by negative, then that is a negative, right? So which is not a good news. So that's the thing actually. That is the idea behind correlation, Pearson's correlation coefficient. You check every sample and find how much that sample is away from the mean. Is it higher than the mean or lower than the mean for x? And similarly, find the corresponding y value and check whether is that higher than mean of y or not. Okay, so that's how it will contribute to the term in the numerator, which gives an idea about whether it is positively correlated or negatively correlated and to what extent. Okay, so I'll say that the numerator is more important because that will determine the sign, whereas the denominator that you have here, which is the variance of x and the variance of y, right? So if you look at what are we doing here, then we are finding out the spread of each x, which we are calling as height in this case, from its mean. And similarly, in case of y, which is our weight in our example, we are finding out the variance or the spread of the weight from the mean of the weight. Okay, and the terms that we have in the denominator, the purpose of these terms is to normalize the value of r. Normalize, or in other sense you can say that to make sure that this value is in between -1 and 1, okay, including. So that's the purpose of our denominator. All right, I hope that this is making sense. Let's move on. Now we will look at some examples and try to reason that why do we have this value. So seems like there were some experiments which were done, and we have the value for the student's SAT score and the GPA of the student, and the student is freshman. And it was found that the Pearsons correlation coefficient for this data was 0.47, which I believe is a reasonable correlation. If it was close to 0, then I'll say that the SAT score does not correlate with the GPA. So if you give me the SAT score of a student and the R was very close to 0, then I'll say, well, I won't say anything about the GPA of a student, because the correlation coefficient is pretty low. But since this is a reasonable correlation coefficient, which is 0.47, then I can say that, on the basis of this strong correlation, the student who has has a better SAT score will end up getting a better GPA. Okay, so let's move on to another example. So this SAT score was also checked for correlation with economic status. Okay, and let's look at the value. So this value is also a decent value, which is 0.42, right? So that means the SAT score correlates well with economic status, which will mean that probably the students who are doing well, scoring well in the SAT score, they are well off, they are studying well, they have all the resources, right? So yeah, we can reason about that, right? So yeah, but it means that yes, these two variables, which are the SAT score and economic status, they are correlating well, because that's a good correlation coefficient value. Okay, so this is an example which I was trying to give you when I was showing you the different scatter plots. So income and coronary disease, right? So when you have the income of different people, and then you're looking at the history, do they have coronary disease or not, and it was found that the correlation coefficient was negative, minus 0.717. So what's the reason? As I showed you in the previous graph, let me take you back. So it could be something like this. Okay, you have income right here, so you can say income, and then on the y axis you can have the disease. All right, yeah. So this is anti-correlation. Like higher the income, the lower was the history found. Okay, so even this is important. Although this is negative, but even then it is important. And how about smoking and mortality rate? This is a higher positive correlation. That means the more a person is smoking, the higher the chances of the death of the person is, right? The higher is the mortality rate. If you find higher tendency for smoking in a community, then you will find a higher mortality rate in that community. So this is positive for that reason. How about the last case, which is about video game and violent behavior? Seems like there was some data available which showed how much people with the violent behavior were playing video game, And interestingly, it came out to be a positive correlation, but the positive correlation is not very strong. Although this is positive, so there is some correlation between the violent behavior of the people and the amount of video game that they are playing. But this is not very strong as compared to the previous correlation values that you saw. Okay. Alright, so now let's learn more about correlation. So correlation is very important actually. Alright, so well, it gives us some idea about the predictive power of one variable for the other, but there are even more things which are important about correlation coefficient. So let's look at this factor which is called R square. Okay, so what is R square? This is very important, so please try to understand that. Now R, we found R, right? That is correlation coefficient. We have looked at the Pearsons correlation coefficient, so let's discuss from that point of view only. So I will read it and then I'll explain to you. That will be better, I believe. So the square of the sample correlation coefficient R square estimates the fraction of the variance in Y which is explained by X in the simple linear regression. Alright, so this is very interesting, very important, so please try to understand. Now if someone is giving you the value of R, then please square that, and after squaring you will get an estimate of how much the variable X is telling about the variation in the value of Y when you use the linear regression. Okay, so right here if you pay attention to the plot, then the plot is also conveying the same thing. So well, on the x-axis we have the Pearsons correlation, and on the y-axis we have its square. Alright, so here if you pick any value like 0.6, then the corresponding value right here would be 0.36. Alright, so that means 0.6 correlation coefficient will be telling about 36% of the variation in the value of Y. So the variance or the variation in the value of Y is what R square will predict when you are using linear regression. So this is important. It might take you multiple attempts to read it, but that's the information. The square of the sample correlation coefficient estimates the fraction of the variance in Y which is explained by X, or the linear regression, whatever you call it. Okay, so that is kind of conveying like how much information do you have in X, how much useful is your regression that you are doing. Okay, so thus the predictive value of the correlation decreases quadratically with R. That's the same thing, right? Its growth is quadratic, so if you go down, then it will reduce quadratically. Alright, so that's what we have. It's the quadratic increase and quadratic decrease. So let's take an example to understand this fact. So if somebody is saying that the correlation between the height and weight is 0.8, then if somebody is saying that R is equal to 0.8, now what do you say, how much of the variation in the in the height can be explained by weight? Okay, so this is between height and weight. So assume that you have weight in X direction and you have height in Y direction, and somebody has given you the R as 0.8. So the formula says that R square, compute R square, which will be 0.64. Alright, so that means 0.64 percentage of variation or variance in height would be explained by weight. Okay, so that means 0.64 variance, right? The variance is important, so please keep in mind it's the variance which is explained by R square. Okay, so that means if you look at 0.64, then it can be approximated, then it is very close to 2 by 3, which is I believe 0.66, right? So that means if you have a correlation coefficient of 0.8, that means it can explain about 2/3 of the variance in height, okay, or similarly for weight. So that's a very interesting interpretation of R square. If R is very small, definitely R square would be a lot smaller, and R square being very small means your linear regression that you have is not good. So the independent variable that you have is having very less you know is explaining very less about the variation in the uh, dependent variable. Okay, so let's look at this further and try to understand like what this R square really means and how did we get to this point. So just to justify, right, just to give you some idea about how did we reach out to this conclusion that R square explains some R square explains the variance in Y. So well, let's look at few more terms that relates to R square. So here we have, although it's not very clear, on the we have X right here and we have Y here. Alright, and assume that we have a regression line. So here the value of R is also given. So as you can see that it's very we see a strong positive correlation between X and Y, and if somebody is saying that it is 0.94, I won't be surprised. So what would be the result, right? So let's try to identify that how much of variance in Y is being explained by X right here. So if you stick to the formula, then you can do its square and you will find out that 88.4% of the variance in Y is explained by X. But let's try to understand how did we come to it. So you can, if you pay attention, you will figure out that if we look at the range of the value that Y is taking, then the Y is taking the smallest positive value that could be probably minus 0.5 here, and the maximum could be little higher than 0.57, we can say, right, just approximating. That's the maximum value that Y is taking. Okay, so we have to look at the variance of Y, which is being explained by X here. So what do we do? This is X versus Y, X and Y. Now there's something called as residual, right? So we need to look at the residual. What is a residual? So we have this real data. All the points that you see here in the scatter plots are the real data, is the real data. And then you see a red line which is passing through the data. So this red line that you're looking at is fx. Alright, so this is the regression line that we have got, the best line that is describing this data. So the point is, what is residual here? So residual is this difference. Okay, so this is one residual. What is it? The real value, which was y, minus f of xi. This is the residual. Alright, so the difference of every point from what was predicted. Alright, so you can similarly, find out the difference between the y and corresponding fx. Fx is something which this regression line is predicting for the corresponding x value. So how good is this line a fit for this data that will be evaluated by computing the residuals, which is y minus fx. So on the right hand figure, if you look at, we are plotting the residual, right? So you this thing right here, which might be difficult for you to read, is in fact y minus f of x. Alright, so look at the distribution of y minus fx. So y minus fx, its mean is around 0, and look at the variation. This variation is very small, right? So if that was the the smallest value, so it is similar to 0.2, and here also it is similar to minus 0.2, and this is 0.2. Okay, so here the range was almost 1, and here the range is 0.4. Okay, and being a variance which is a square term, so if you find out this ratio, which is the variance of residual, VR means the variance of residuals. Alright, so right here when you find out the variance of the residuals divided by the variance of y, okay, when you find out this ratio, then this ratio is equal to 1 minus r square. Alright, so right here this variance of residual is very small, that is very close to 0, so you can see that r square is very close to 1. So this is the expression from where we come to the conclusion that this r square, if you find it out, will kind of explain the variance in y as the function of x. Okay, or as explained by x, not as a function of x. You should say r square will give us the information, or the estimate of r square will give you the estimate of the fraction of variance in y, which is explained by x. Okay, so these two slides are related. If you want to get into the detail, like how did we come to r square, and the fact that r square is giving an estimate of the fraction of variance in y, then that's how we got to it. And what you need to really understand is that what is r square and its significance. That should be sufficient. If you want to understand this thing, yeah, you're welcome to. Alright, so let's move on. Now this is an interesting thing about the significance of correlation. So the point is that somebody gave me the data, and I know the expression of the Pearsons correlation coefficient, and I computed R, and I'm excited about R. Now how should I consider that as meaningful, right? So how do we determine that the correlation value that we are getting is significant, right? So for that significance, we have an interesting plot right here. So let's look at this plot. So here you have some sample size, and you have Pearson's correlation coefficient. So an interesting thing you should see is that we have a decreasing plot, right? So for very small sample size, we have a higher value of correlation, and as this sample size gets higher and higher, the correlation is dropping. So what does it mean? So it means that what it means, this plot means that when you have a very high sample size, or a sample size close to 250 or 300, let's think of a point as 300 right here, and if you go further down, then probably you will reach to 0.1, okay, or let's say 0.5, let's approximate. So it says that if your sample size is more than 250, then probably 0.15 is a reasonable correlation coefficient. Okay, and this is when we are keeping the significance value, which is alpha, as 0.5, right? So the traditionally, right, using a typical statistical stand which deals with the significance value that we call as alpha, and don't worry about significance value and all these things, because probably we will discuss that in hypothesis testing when I'm teaching you. So this result that you have in this plot is based on alpha value as 0.05. That means the chance that these correlation values are obtained by or obtained on any random data is less than 5%. Okay, when that is the case, then it says that when your sample size is close to 300, then 0.15, which I am getting from here by approximating, is a good correlation coefficient value. Okay, But the interesting thing about correlation coefficient is that it not only depends on the size, but it also depends on R. Okay, although this value is small, and you are saying that the sample size is big, so you are fine with it. But the problem is that when you compute R squared, this is going to be very, very small. And when R square is very, very small, say very close to 0.1, okay, when it is close to 0.01, that means it is only explaining 1% of variation or variance in Y. Alright, so which is not good. So that's the point. The point right here is that the statistical significance of correlation depends on the sample size as well as R. So the point is, you should have a large sample size, and at the same time the value of R should be also high. Why do we want value of R to be high? Because if R is small, then R square is going to be further small. And when R square is very small, then it will not be able to explain much about, it won't be able to give a good estimate of the variance in the dependent variable or Y. Okay, so this is very important fact, which says that the statistical significance of a correlation coefficient depends on sample size. If the sample size is small, then that's not a good news. You should have a decent sample size, but at the same time the value of R should also be high. It should not be low. If the value of R is low, then R square would be even lower. And if the R square is lower, then you will not be having a good estimate in the variance of the value that you're predicting. Okay, so I hope that this is making sense, although this is little intense, but if you stick to the definition, if you try to understand the definition, then I think this is cool. And if you have questions, please don't hesitate in reaching out to me. Alright, so we have looked at one correlation coefficient, which was Pearson's correlation coefficient. Let's have a look at another correlation, which is called Spearman-Rank correlation. So this is somewhat different from the Pearson's correlation, because Pearson's correlation is kind of it's kind of based on fitting a line through the data set, which is kind of related with linear regression. We want to fit a line through the data set, and then we try to estimate the correlation. But in case of a Spearman's rank correlation, it's based on a different concept altogether. Okay, so let's try to understand, like, where will this be handy and how do we compute that. So this correlation coefficient that we have is not based on the concept like Pearson's correlation, where you look at each sample and try to see where exactly that sample falls in terms of X, in terms of Y from the corresponding mean, and then you use the variance and you divide that. So here we have a different concept, so where it looks at the ranking. So there we have a concept of ranking. So let me read these slides, these points, and then I'll explain to you how do we do that. So it counts the number of disordered pairs. So disordered pairs that you have, that relates with ranking. Okay, so we have to do a ranking. That's the reason we call it rank correlation. So once you have this ranking for X and also for Y, then what we do is we count the number of disordered pairs. Disordered pairs means if X is say rank 5 but Y is rank 3, then we'll have to find out the difference in the rank. Okay, so that's how this is computed. It is not based on how the data fits the line. So this fact of data fitting the line is something which is used in Pearson's correlation coefficient. In Spearman, we don't look at how the data is fitting a line. We just rank the data in terms of X and Y, and we look at the agreement between the ranks in X and Y. That's the reason we call it Spearman rank correlation. Now, why do we need that, right? So you might wonder that peer the previous Pearsman correlation coefficient was cool, fine. Why did we need this? So there are certain cases actually, as we said that right here in the first point, that Pearson's correlation coefficient is based on this concept that we try to fit a line in the data. So often there are cases where the data may not ideally fit in a line, like this figure, right? Pay attention to this figure here. So what do we have here? We don't have one perfect line fitting the data, right? So if you try to fit a line, the line will fit like this, which is not perfect, right? Whereas you can see a trend here. As the x going up, your y goes up, right? So in place of one line, we can have two lines which will approximate this data. Okay, so in these kind of cases where we do see that there's a correlation between x and y, if I call this x and I call this y, then yes, we do have the correlation, but it's not captured by one straight line. So in these cases, our Spearman rank correlation will work fine. Okay, it will come up with the value like 1.0. So we have the value for Spearman coefficient as well as Pearson coefficient computed for this data. Okay, and since as you can see that there is a correlation, right? A reasonable correlation between x and y, and that's what is being captured by Spearman coefficient, whereas Pearson coefficient doesn't get the perfect 1.0 because its concept is different, right? We are looking for an ideal line to fit the data. Okay, so how do we compute this? We'll get to that in the next slide. Now, you should always keep these things in mind, like what is the concept behind one correlation coefficient versus the other, and when will we use one correlation coefficient versus the other. Okay, so the point right here is when should you use Spearman rank correlation. So it's better when non-linear relationships occurs, right? So this is not linear, this is non-linear. In fact, there are two lines which are describing this data. So here our Spearman coefficient is better compared to Pearson. And certain cases when when the data is linear, both are good, right? So you can see that Spearman is giving a good value, and the same value we are getting from Pearson coefficient also. And there's another case if you have outliers. So for outliers also, our Spearman rank correlation is better. So here we have an outlier, you can see right here, and this is not susceptible to outliers. Spearman rank correlation is stable with outliers, whereas in Pearson's coefficient you can have a problem. So, and that's what is being reflected by these values also. Okay, so even for outliers and for non-linear relationships between the data, we should go with Spearman rank correlation. Okay, now let's look at how will we compute that. All right, so there is something called as ranking. So assume that you had x, y, x was your height, let me call x as height and y as weight, and let me put some values right here. Okay, so 160, 180, 170, 182 and 165, 175. These are some arbitrary values that I'm putting in. Then you can have 156 the height and maybe 170 the weight, and one more sample, 180 and 190. So once you have these values, what we need is ranking for each. Okay, so what I should call, I should have RH, rank for height, and RW, which is rank for weight. So what do we do here? Let's stick to the ascending order. So it says that we have to give them a rank. from 1 to n, and if you read the textbook, then according to the textbook we should go from lower to higher. So the lowest value should get a rank of 1 till the highest, which is n. So here the smallest is 160 in terms of height. The smallest is this guy here. I'll give it value 1. Then the next smallest is, I'm doing the ranking for height. Okay, for weight I'll do here. So for, then you have the third value right here, fourth here, and fifth here. So you need to do this ranking first, and let's see what's the smallest. Smallest is right here, 1, and then you have 2, 3, 4, and 5. Alright, so from the values that you have for x and y, you need to come up with the ranks for x and ranks for y. So this is the rank for x, and here the rank for y is right here. And then you have to compute the difference in these ranks. So there should be another column where you'll find 2 minus 3 or 3 minus 2. Alright, 4 minus 4, 3 minus 2, 1 minus 1, 5 minus 5. Alright, so the DA factor that you have here in the Spearman correlation coefficient, this will find the difference in the rank of these two attributes that you have in your data, between which you want to find out the Spearman correlation. Alright, and then this difference that you have is to be squared, and it is to be added for all the records. And then once you have computed this di square, then you can put that in this expression where this is 6 times the summation of di square divided by n into n square minus 1, where n is the number of sample. N is the number of sample. Alright, and this is 1 minus the row that you have. Row is your Spearman correlation. Is computed as 1 minus this expression, which is based on the summation of di square and 6 times of that divided by n into n square minus 1. Okay, and interestingly, its value is in the range of minus 1 to 1, the way we had for the Pearsons correlation. This is an interesting stuff. Alright, let's move on. Okay, so now since we have looked at two correlation coefficients, the Pearsons and the Spearman's rank correlation, let's look at the correlation and see what should we, if we have a strong correlation, then what does that signify? Excuse me. Okay, so there is a warning actually. Often we are misled by correlation, and we reach to the conclusion when we see a very good correlation. Now the warning is that the correlation does not imply causation. Okay, correlation and causations are totally different. From a strong correlation between x and y, say x is a variable, y is a variable, we should not try to conclude that x results in y or y results in x. Okay, so this is something we cannot say by just looking at correlation. So there you have some interesting web comics, so read through these, and these will tell you the same thing, that correlation does not imply causation. So let's look at an interesting scenario, right, which will help us in understanding the fact that we can have correlation, but that may not imply a causation. So the number of police active in a neighborhood will be strongly correlated with the crime rate. Okay, so if you have the crime data, right, crime data is also very popular in data science. A lot of analysis has been done on that. So you might find that the places where you have higher crime, you'll have a lot of police posted over there. But police being present at a site where there was a crime does not mean that the police is responsible for doing the crime. Okay, so this causation kind of a thing does not imply from correlation, right? So the number of police active in percent correlated strongly with the local crime rate, but the police do not cause the crime. Okay, so that's an argument, very strong argument, and which should kind of help in understanding that the correlations do not result in causation. So we should avoid using a correlation to come up with some result like this caused that. Okay, we will only use correlation in making some predictions. Okay, and predictions are not causal kind of a thing. If we see that x is strongly correlated with y, then we will use the value of x for predicting the value of y. Alright, so let's move on to another interesting topic which relates to time series. And time series is again a very rich research area in data science. And we have a concept of correlation in time series, but we call that autocorrelation. Okay, so autocorrelation is a very popular technique which we use in the analysis of time series. So assume that you have some data of a stock, right, or maybe the data for the flight passengers, and you want to find out like in what season we have the highest passengers flying. So for all these kind of analysis we use autocorrelation. And there is something called as periodicity or seasonality in that time series data. So let's try to understand like what is autocorrelation, how does it relate to correlation, and what can we do with it. So the time series exhibits something called as cycle. Okay, so let me show you an example. So here we have the number of passengers flying, and we have the data for month. So if you look at the trend, this is time series data, okay, because we have number of passengers varying over the time. So this gives you a nice curve which is a time series. Now if you pay attention to this time series, you should see a pattern, right? Pattern repeating. The same pattern is repeating. This thing is called seasonality. Seasonality, which is a term in time series, and it's related with cycles, right? If you look at that, then this is a cycle, this is a cycle, this is a cycle. So if you could reason, right, so you'll be able to reason yourself, and you'll be able to answer that, why do you see the seasonality or the cycles in the passengers over the period of time? Well, because we know that we have over the whole year we have some vacation period where people fly a lot, right? So that kind of a thing is reflected in this plot. Now from data science point of view, we have this task like we need to make predictions in the time series, and the prediction would be meaningful only when we take into account these seasonalities, right? So all these things are important, and related to that is this concept of autocorrelation. Okay, so what is this autocorrelation? So time series data often exhibits cycles which affects its interpretation, right? We have looked at that. Now sales in different businesses may well have 7 days, 30 days, 365 days, or 4 into 365 days cycle, right? Now we looked at one cycle, right? We looked at one cycle in this figure. Now you can have other kind of cycles as well. So the important thing in time series data analysis is to identify the cycle and the period of the cycle. Is the cycle repeating after 7 days, or is the cycle repeating after 30 days? 7 days means there is some seasonality which is happening over the week, right? Just think about this case. If you have the data about the number of customers coming to a restaurant, and if you have that time series, probably you will find a seasonality with a period of 7 days. How about this, that the restaurant has a really high customer number on weekends, so that is possible, right? So in those kind of cases you can have the seasonality for 7 days also. Similarly, there can be some case, we can have 30 days seasonality also. 365 days is very common, because just look at some events happening around Thanksgiving, or the events happening around Christmas. So these are annual events. So if you want to find that kind of a trend, like the demand of Christmas tree. So if you have that data over a number of years, then you should see the seasonality after 365 days. All right, because if somebody is buying, if the demand for Christmas tree is high around say December of 2019, then the next time it will be the same demand or high demand would be in the time around December of 2020 and then December of 2021. All right, so that's the point. Actually, we need to find out the excuse me, and this cycle, like after how many days we will have the same scenario. So that's the important thing, finding out the length of the cycle, like k. Okay, k is 7 here, 30, 365, right? So now the point is, how will you identify the cycle length k? That's the thing, right? So for that thing to happen, we need something called as autocorrelation, where we find the correlation between the time series itself, between two data points taken at the time t and the second one taken at t plus k. What is k? K is the period of the cycle. So if you're looking for weekly autocorrelation, then you should look at st and st plus 7, because you're looking at the cycle of length k. So the important thing in this discussion is identifying the length of the cycle k, which varies, which depends on your application, okay, and also the concept of autocorrelation, which means finding the correlation with itself over different time interval, right? So the correlation between the point between the time t and the correlation at the time t plus k. All right. So how will that happen? So if you are arbitrarily taking points and taking some values of k, where k is changing, and you're finding out autocorrelation, then you will find a high or a large autocorrelation only when you have this reasonable value of k. Alright, so that's the point. A cycle of length k can be identified by unexpectedly large autocorrelation between st and st plus k for all, right? So as I was giving you the example, if we have a person from a different planet who comes to the earth, and we give the person some shopping data, and if the data is about some very specific item like Christmas tree, and that guy is looking at and plotting it, right? So that guy is plotting the number of demands for Christmas tree over say 10 years. So that person would easily be able to identify a spike around December time, right? So that way you can identify this thing using the autocorrelation. I hope these things are making sense. All right. So, well, autocorrelation is is an expensive process, but fortunately for us, we have some algorithms based on fast Fourier transform. So using that, it becomes very efficient. All right. So let's go to the logarithms, which is very important concept in data science, and let's try to understand like what is log. Alright, so as it has been said that log is the inverse exponential function. Alright, so let's try to understand that with the help of an example. So if I have a number y as 1000, alright, so y is 1000. Now how can I use okay, y is 1000, which I can write as y is equal to 10 to the power of 3. So what I am doing here, I am using exponentiation. Exponentiation I am using. So given a base, the base here is 10. So what I did, I used a function called exponentiation, and when you said the x is 3, then what I did, I knew the base was 10, I did 10 to the power 3, and I got y, right? This is exponentiation or exponential function. Log is the inverse of exponential function. So what does that mean? If somebody says that y is 1000 and base is 10, so what is log? Log of y, right? So see, what is exponential function? You tell me, you give me exponent value and give me the base. So I will put the exponent on top of base, and I will compute 10 to the power 3, right? Exponent, you say x is equal to 3, I'll say y is equal to 10 raised to the power 3, which is 1000. What is log? Log is the inverse. So what log will do, if somebody says that now y is equal to 10 to the power 3, find its log. So in log you will return the exponent. Alright, so what will happen? Somebody will say, compute the log of y, and that person should also provide me a base, which is 10. Right, so what should I return? I should return the exponent. Alright, so I'll say log of y to the base 10 is equal to 3. Right, so that's what we mean by the fact that logarithm is the inverse of exponential function. Okay, good. So let's look at some scenarios. We have y is equal to b to the power x, right? Let me solve this here. Y is equal to b to the power x, right? So we are generalizing this discussion. B was 10 here, but let's change the 10 to any b, which is a general thing, and this is the exponential function. Now what is log of y? So log of y given base b would be equal to x. Alright, the inverse of that. We are getting x, and what is x? X is the log of y to the base b. Alright, so that's what we have here on the left hand side. X is equal to log of y to the base b. So this much of logarithm is important for you to understand. Now, if you follow this thing, now we should look into the cases like why are we discussing logarithms in data science course. The reason that there are a lot of places where we will use logarithms. Alright, so let me take this example of probabilities and tell you like why do we use logs when dealing with probabilities. Now, this could be a very interesting question for you, like what would be the sign of the log of pi? Pi could be any probability, right? Pi means probability, any probability value. So if you are following me along, then you should see that you should be able to understand that the maximum value that the probability can take is maximum probability is 1, and what is log of 1? That's a 0. Alright, so any value which is less than 1, maybe even 0.9, will have a negative value, right? So log of a probability value is mostly negative. That's an interesting thing. Okay, good. So leaving that aside, let's think about the scenario like where dealing with the probabilities log will really help. Now when you're dealing with the probabilities, a lot of probabilities, and you're multiplying, right? Say I have 5 probabilities. I'm multiplying p1 into p2 into p3 multiplied by p4 multiplied by p5. Now all these pi's that you have would be less than or equal to 1. Probability cannot be more than 1, right? So you can see that this multiplication of probabilities would really would tend to decrease, right? So when you multiply a lot of probability values, then the value becomes very small, so small that it gets very difficult to represent that on computer. Alright, so that's the problem. That's what we are saying, that the log of probability is more numerically stable than multiplying probabilities. So if you are multiplying the probability, real value of probabilities, then you might struggle to represent that properly in computer. So what is the solution? The solution is that let's not keep the real multiplication of the probabilities. In place of that, let's keep the log of the multiplication of the probabilities. Alright, so if you know the basic logarithms, then you'll find this really interesting. So what do we have here? Assume that, right? Pay attention to this side. Assume that I have to multiply n probabilities. So this symbol, I hope you understand, this is for product. Pi. Probably you are familiar with sigma, which is for summation. Sigma is used for summation, pi is used for multiplication. So what does it mean? It means that we have n probabilities and I want to multiply all those n probabilities. P1 multiplied by P2 to P3 goes on till n. I'm multiplying n probabilities. Now this will be a very, very small number. If n is equal to 10 or maybe 5, it will be very small. So if I don't want to do this, rather I want to compute its log, then what should I do? Alright, so if you know the basic principle of log and you are doing log of pi, p1 into p2 into p3 into p4 into p5, then that would be same as log of p1 plus log of p2 plus log of p3 plus log of p4 plus log of p5. Alright, so when we compute the log of the multiples, then that results in the summation of log of each values, right? So this converts to log of p1 plus log p2 log pn. So that's what we are doing here. When you do the log of this expression, then that will boil down to the summation of I is equal to 1. You do the log, okay? When you do log, then that is equal to summation of I1 to n log of pi base b. B is some base that we are using. Alright, now when you can do all these things, right, what is p? P is this term. P is in fact the log of the probability that you were required to compute. Now you did this exercise, right? You converted the product of the probabilities to the log of the product of probabilities which you computed, and you stored that in P. Now the question is, how will you get the real probability if you want to? Well, the answer to that is simply raise this P to raise the base B to the power of P. Okay, so that's what we have here, and that's your final probability. So it's so much interesting. Alright, so that's the trick with logarithms. Alright, so we have one more interesting case, or two I'll say, about logarithms and their application in data science. Now sometimes when you're dealing with ratios, then it helps if you use logs to represent the ratios. So the example right here is that if you have some ratio in your data set, and very often you will be dealing with the ratio value, and the ratio is about the new price versus the old price. Now the interesting fact is that if you have a scenario like 200 is the recent price and 100 was the previous price, then if you look at the increase in the price, then this is 200% from the baseline. Okay, but if you're thinking about 100 being the new price and 200 was the previous price, then this is 50% below the baseline, right? So see the difference. If in the numerator it is 200, then that is 200%. If in the denominator it is 200, then that is 50% below, right? So that seems like a little unfair. So what's the best deal actually? If instead of dealing with this data as raw data, raw ratio data, if you convert that to the log, to the base 2, then it will be more meaningful. Why are you saying more meaningful? Because now if you have 200 divided by 100, which is 2, and if you take log of 2 base 2, then that is 1. Alright, 1 is log of 2 base 2. Okay, that is 1. And how about minus 1? Minus 1 is log of 2 base 1 by 2, minus 1. And how about the case when it is 1? You have 0. Right, 0 will correspond to log of 2 base 1. So this is more meaningful, right? So we have kind of equal displacement. Treating the ratios as logs will result in having the equal displacement in the case like this, and that's what we ideally need. Okay, so that's another interesting case of ratios. And then another interesting point that the author, Professor Skinner, has pointed out in his book, and it relates with their previous experiments where they were comparing the performance of two algorithms. And so what happened initially, the result was quoted with the original ratio, and that's how the result looked like. And this seems to be the performance of two approaches, A versus B, the ratio of A versus B, and the result is on 4 data sets. So when you look at the original ratio, then you can, the only thing that you can probably understand is that this result seems to be an outlier, right? But that's problematic because you have too many points squeezed right here. Okay, so you can't say much about that. So what should be done for ratio data for the better interpretation? That should be converted to the logs. And when they transform this whole result into the log, then this is what they saw. Now see that these two pictures totally different. This point that looked like an outlier doesn't look like an outlier anymore. And these points which were kind of looking okay happen to be the outliers, right? So this kind of insight you will find about the ratio values when you take the logs. Okay, so that's an interesting insight to have about the ratios. When you're dealing with the ratios, better convert them to the logs. Now another application of the log, right? So I think we have looked at 3 applications of logs. One, dealing with the probabilities, which probably we will encounter when we will discuss the Bayes classifier, right? So there we will look at I think the log of probabilities. And then first was taking the log of probabilities so that we can have a stable representation. The second one was about ratio, we just saw. Now the third one is about power laws. So very often when you're dealing with the data set, you will come across the data with the skewed distribution, and the skewed distribution is not a good news, right? So here in most of the cases what happens is that when you take the when you take the log of the data which has a skewed distribution or a power law distribution, then it often changes to a normal distribution. And we love normal distribution in data science and machine learning for the reason that normal data which is distributed normally has more predictive power because it results in a better spread of the data. Okay, so taking the logarithm of a variable with power law distribution brings them more in line with the traditional distribution. Traditional means probably the normal distribution. So as an example, you can, again, it's from the textbook. If this, let's look at this, example also, because in this example also I'm looking at the same data, which is the income. Right, so if you look at the income, then this income doesn't look like is a skewed distribution, right? A lot of people you have with a low income, whereas the number of people with higher income is very, very small. Okay, so this is not an ideal distribution to have. But when you take the logarithm of this based 10, then you find something very close to the normal distribution, which is a good news. Alright, so this trick helps. If you have a power law distribution, apply logarithms, you might end up with a much better normal distribution. Alright, so the same point has been mentioned here. A normal person's wealth is roughly the same number of logs from a typical student who's probably not earning much as of that person's from the Bill Gates. So the point is that the Bill Gates earning is really huge. Now if you have a normal person and if you compare the salary of that normal person from the Bill Gates actual salary, then the difference is huge. But when you transform that using log, then probably the difference in the salary between the Bill Gates and a normal person is same as the difference in the salary of the normal person to a typical student who's not earning much. So that's the point, that's the message about it, that log really helps in dealing with the really skewed data, very often the data that follows the power law. Okay, and that was it. I will stop right here and I'll see you in the next video lecture. Thank you. Bye bye.